AP Chemsters, this is Mrs. Vanderwally bringing you another edition of the Chapter 16 Blank Wall edition. Section 16.3 says the effect of temperature on spontaneity. Back in the first time we even talked about thermodynamics, we talked about the idea of temperature. And temperature is related to the kinetic energy of the molecules. And so if temperature gets greater or is higher, then those molecules are going to move faster. And putting this in reference to spontaneity and entropy, that the faster these molecules go, then the more disorder, the more probability of them being more random is going to be greater. So there is a link to temperature and the idea of entropy and spontaneity. So let's see what this says here. Direction of heat flow. So entropy changes in the surroundings are primarily determined by heat flow. Exothermic reactions in a system at constant temperature increase the entropy of the surroundings. So there I wrote, so if the heat is going from the system to the surroundings, that's where we had delta H is negative, and now the surroundings are going to be warmer. So the surrounding molecules are going to go faster and there's going to be more disorder. How about the opposite? What's an endothermic reaction? That literally means heat coming in. So the surroundings are going to let its heat flow into the system. And so now the surroundings are going to get colder. So that's where delta H is positive. Let me write that down. So if the surroundings are now colder, the molecules are going to be moving more slowly, and there's less chance of randomness, if you will. So the entropy of the surroundings also goes down. And it says the impact of the transfer of a given quantity of energy as heat to or from surroundings will be greater at lower temperatures. So temperature itself has an impact on this transfer of energy. So let's kind of see what's going on here. Driving force provided by the energy flow, the heat. So the heat is equal to the magnitude of the entropy changes in the surroundings. So they are related by this quantity of heat J over temperature. And we said quantity of heat was your delta H. So talking about the surroundings. So in an exothermic reaction, that means heat is going from the system to the surroundings. So the surroundings is getting more random, and that's why delta S is a positive number here, because it is going to be a greater disorder. But wait a minute, I thought exothermic was a negative delta H. But here it's a positive number. It's the opposite, if you remember, that the system and the surroundings are opposite of one another. So let's go to the next one. So an endothermic reaction. So that's where the heat is going from the surroundings to the system. So the surroundings are getting colder, and so their randomness, their disorder is actually decreasing. There's less randomness, and that's why we have a negative sign there. And so if you put it together, again, notice that the delta H surrounding has this negative sign here. It's the opposite of the delta H of the system, and typically we will calculate the delta H of any system. So it's the negative of it. I guess I erased, or I circled my equal sign, not my negative sign. Sorry about that. So in summary, let's see what's going on here. Exothermic reactions in a system at constant temperature. Think about it. Think heat going from the system to the surroundings. What's happening to the entropy of the surroundings? Hopefully you got it. It goes up. All right, what about this one? Think about it. Endothermic, that's where the heat goes from the surroundings to the system. The surroundings get colder. So if they are colder, what happens to the entropy? They're going to move slower, and they're going to have less randomness. And so the impact of the transfer of a given quantity of energy as heat to or from the surroundings will be greater at lower temperatures. Okay, so let's turn the page here. What's happening? This says in the metallurgy of antimony, the pure metal is recovered via different reactions depending on the composition of the ore. Calculate the delta S surroundings for each of these reactions at 25 degrees and 1 atmosphere. So iron is used to reduce it, and there's my delta H. So they want to know what is going to be the delta S of the surroundings. Well, we know that delta S of the surroundings is equal to, the surroundings, negative delta H over T. And what unit does T have to be in? Joules always. So it's the negative of the negative 125. So it's equal to negative 125. But wait a minute, that's in kilojoules. Typically, S is measured in joules. So let me go ahead and convert that into joules. Over 25 degrees Celsius, which is 298 Kelvin. Hopefully you knew that. And now that's equal to 419 joules per Kelvin. Notice that is a positive number. That means the surroundings are getting more disorderly. There's more randomness to those molecules. But what about the next one? Carbon can be used as a reducing agent for oxide ores. And there's your delta H of the reaction. So if I were to do that, delta S of the surroundings is equal to negative delta H over T, which is equal to negative 778,000 joules over 298 Kelvin again. And now notice what we get. We get 2610 joules per Kelvin. This is, oh, I'm sorry, I forgot the negative. This is a negative number. So what does that mean? The surroundings are becoming less disordered. Okay. All right, now let's put this together and let's talk about the free energy, also called Gibbs free energy. It is the total picture of spontaneity. This is the absolute yes or no, is this reaction spontaneous or not? So calculating free energy change, and here's our equation, delta G equals delta H minus T delta S. You can kind of see how that equation came to be. In a sense, you multiply both sides by T, and that kind of works around that equation that we just used. So H is enthalpy, K or T is Kelvin. Free energy and spontaneity. Check this out. This is really important. Reactions proceed in the direction that lowers their free energy. You want delta G to decrease. You want the change to be negative. Equilibrium occurs when delta G equals 0. That same equilibrium that we spent the last 3 chapters covering. So let's kind of check out how this works in the equation. So if delta H is negative, minus T delta S, and if delta S is a positive number, if you have a negative minus a positive, think about it. No matter what the temperature, what will delta G be? Think about it. Yes, delta G will always be negative, therefore it will always be spontaneous. And that is true at any temperature. It will definitely favor the products. You will have that reaction go to completion if you have a negative delta G. Now, what about the next one? I'm going to erase this up here. What if delta H is positive? Minus, and temperature is always positive. That's why we use Kelvin. There is no negative Kelvin, so that's not going to change the sign at all. And what if S is also positive? So if I have a positive number minus another positive number, can delta G be negative? Yes, it can be. But what has to be a bigger number? This term has to be bigger for that to be a negative number. So when will that term be negative? Well, that's at a high temperature. That's when minus T delta S will be a bigger positive number than the delta H. And that's when that whole term is going to be negative for the whole delta G to be negative. So when you have an endothermic process, but you're still increasing the randomness or the disorder, that will be a spontaneous process if your temperature is high. All right, and this, hopefully if your temperature is high enough, then it will favor the product. If it's not high enough, it won't. All right, so what about the next one? What if we're back to the endothermic process again? So this is negative, but now your entropy is also decreasing. we're back to square one again. So when will this be a negative overall? If delta G is negative, what has to happen? That it all depends on temperature again. If temperature is an itty-bitty number, so T is low, then it is a spontaneous process. All right, if T is too high, then it's not spontaneous and you won't favor your product. Finally, what if the two items that are very unusual work together? What if this is a positive number minus T times a negative number? No matter what, what's a negative times a negative? It's going to be a positive. No matter what the temperature is, you're going to have a positive delta G, and this is never spontaneous. So at any temperature, I don't care what it is, it will never be spontaneous, and if anything, if it's not spontaneous, you will just have your reactants left. You're not going to make them do anything. You're just going to sit there with your reactants. So this chart is super duper important. So think about it, play with some numbers, if you will, until you really understand this chart. It's just number theory. When will you get a negative number? When will you get a positive number? Okay, so let's go ahead into the next. All right, problem number 7. At what temperature is the evaporation of liquid bromine spontaneous at one atmosphere? And so now we're asking, at what point is the temperature going to make that difference? Look at these signs here. Notice that delta H is positive. Notice delta H is positive. That's endothermic. That's not a typical scenario. However, your randomness is getting bigger. So if you go back and look at the chart from the previous page, when we have endothermic and we have an increase in entropy, what does it depend on? It will be spontaneous if you have a high temperature. So this can work. So let's try this. So delta H, or delta G, excuse me, is equal to delta H minus T delta S. And when it's at equilibrium, we said earlier, that's when delta G is 0. So we can solve then, add T delta S to both sides, and now just plug in the numbers. So we are looking for T. It's equal to delta H, which is 31.0 kilojoules, over delta S. I'm going to divide both sides by delta S. So wait a minute, if this is kilojoules and this is in joules, I got to put them both in the same unit. So I'll just divide this by 1,000. And notice my K is still on the bottom. And when I do that, and I actually do your division, why don't you do it too to make sure I did it right, you should have gotten it 333. And so what does that mean? That is when this reaction where the evaporation of liquid will spontaneously work. It wouldn't do it at any temperature lower than that. It will do it at this temperature and higher. So it says, what is the normal boiling point for liquid bromine? Well, this is at equilibrium. And really, that is how you define your normal boiling point, because what's going on at this temperature, we have gases and liquids coexisting. Because if you look at the equation, bromine liquid, spontaneously going to bromine gas. So at K equals 330, or excuse me, at the temperature of 333, it's at equilibrium, so we can actually put that other arrow going in because it's at equilibrium, okay? And that's where delta G is 0. That's it for tonight. I hope you got something out of it. Tomorrow we'll do problems in class, so this is your only homework, is watching videos. Have a great day. We'll see you tomorrow.